So far, our study of the law of conservation of momentum has been limited to motion in just one dimension. Here we'll investigate a problem where two objects collide and move in two dimensions, meaning their motion can be visualized on both the x and y axis. So we'll say that we have an object with a mass of 3 kilograms moving to the right at 20 meters per second, and the center of mass of that object doesn't align with the center of mass of a 2 kilogram object that's at rest at the origin. So what happens in this collision, and this is a hypothetical, we're just making this problem up, but this is a possible outcome, that the 2 kilogram object after the collision moves down into the fourth quadrant with a speed of 15 meters per second. So again, that's our 2 kilogram object. So then the question is, what do we know about the motion of the 3 kilogram object after the collision? Well, momentum has to be conserved even in these two-dimensional collisions. So it might be helpful to take everything we know about the motion before and after the collision and make some sort of a graphic organizer of all of the velocity or velocity components along the x and the y axis. So let's do this. Let's make a grid. And we're going to divide that grid in half so we can represent what we know about the motion along the x and the y axis both before the collision and after the collision. So before the collision we have two separate objects. We have a mass number 1 equal to 3 kilograms, and it collides with a stationary mass number 2 equal to 2 kilograms. And then those same two objects, M1 and M2, move in distinct paths after the collision. Our M1 is 3 kilogram, our M2 is 2 kilograms. So what we want to put in all these grids are the values of the velocity components. So our 3 kilogram object initially has motion exclusively along the x-axis of positive 20 meters per second, and it doesn't have any velocity at all along the y-axis. There's no component to this velocity vector that lies parallel to the y-axis. And then the 2 kilogram object was at rest, so both of its velocity components are 0 before the collision takes place. After the collision occurs, let's say, for example, that this 15 meter per second velocity is directed at an angle of 37 degrees. So we need to find these two velocities. We're just going to call this v subscript x and v subscript y for mass number 1. But we know for mass number 2 that its velocity can be broken into components. Let's look at these components. That 15 meters per second has a component to the right, which would be 15 times cosine 37 degrees. And there's a component to that velocity pointing in the negative direction, and this is going to be negative 15 sine of 37 degrees. Okay, so 15 cosine 37 and negative 15 sine 37. And with your calculators you can verify this is positive 12 meters per second, and this is negative 9 meters per second. So we just want to apply the equation for conservation of momentum as we know it independently along both the x and the y axes. So the equation I'm referring to is the one that says m1u1 plus m2u2 equals m1v1 plus m2v2. That equation can be applied independently on the x and y axis. When we apply that equation along the x axis, we have 3 times 20 plus 0 is equal to 3vx plus 2 times 12. So 60 equals 3vx plus 24. Vx is equal to 60 minus 24 divided by 3. That's 36 divided by 3, or 12 meters per second. Now let's apply our equation to motion along the y-axis. So we have 3 times 0 plus 0 is equal to 3 Vy plus 2 times negative 9, or 0 equals 3Vy minus 18. So Vy is equal to 18 over 3, which is equal to positive 6 meters per second. So what we have after the collision is our object with a mass of 3 kilograms is moving with greater velocity component in the x direction and a slightly smaller velocity component in the y direction. So we've got a 12 meter per second component to the right and a 6 meter per second component upward. So the motion of our 3 kilogram object must be somewhere into the first quadrant. Our 3 kilogram object has velocity of 12 meters per second to the right, 6 meters per second upward, and so its total velocity v can be found from Pythagorean theorem, 12 squared plus 6 squared. In other words, the total speed of the 3 kilogram object is the square root of 180, which equates to about 13.4 meters per second. Now let's try to determine whether this collision is perfectly inelastic, or elastic. Well, we know it's not perfectly inelastic because they don't stick together. So we need to determine whether this represents an inelastic collision or an elastic collision. And that just comes down to whether or not some of the kinetic energy is converted into wasted thermal energy. So let's try to calculate what the initial kinetic energy of the system was. So remember, all of the kinetic energy prior to the collision is only due to the motion of the 3 kilogram object. The 2 kilogram object was at rest. So the total initial kinetic energy is 1/2 times 3 kilograms times 20 meters per second squared. And I think you agree that that's equal to 600 joules. Now, the final kinetic energy comes in 2 parts. We have the final kinetic energy of one object and the final kinetic energy of our second object. So 1/2 times 3 times, we'll just call it the square root of 180 squared, right? That's the 13.4 meters per second that we found. Okay, that equates to 270 joules. And then the 2 kilogram object is moving with a speed of 15 meters per second. So when you calculate that out, you get 225 joules. So if we add those two values together, we get a total of 495 joules. So we notice that, yeah, indeed, some kinetic energy was lost. There's a loss of kinetic energy equal to 600 joules minus 495 joules, or in other words, 105 joules of energy are lost. If you want to state that fractionally, we can say the percent kinetic energy lost, which represents the amount of thermal energy produced, is equal to 105 joules compared to the initial 600 joules, and 105 divided by 600 as a percentage is about 17.5%. Okay, so yep, what we had there was an inelastic collision. Now, one thing I want you to know, if you have a collision in which the one object in motion has a mass that's identical to the other object that's at rest, if the collision happens to be elastic, then there's a special outcome. After the collision, if object number 1 moves off at some angle of theta, then object number 2 is going to move off at some angle, maybe we'll call it phi, but the rule is phi plus theta has to equal 90 degrees in this special case where the masses are equal and the collision happens to be elastic, and I leave that up to you to prove.